Hello everybody, welcome back to another video, and in this video we'll be looking at the integral of secant cubed x, and this will be a good video to watch if you're learning about integration by parts and you're looking at cases where you have repeated integrals. So what I mean by that, well, let's get started. So the first thing that we notice is that we can break this down, this secant cubed, into its other factors such as secant squared and secant, because we know that some a cubed can be written as a squared times a. So what we can do is we can write this as the integral of secant squared x times secant x dx. And now you may be asking, well, why did we do that? Well, the reason why we did this is because we can integrate secant squared x pretty easily, and we can also differentiate secant x pretty easily. And that is the thought process that you have to see when you have higher powers of trigonometric functions, because often there's going to be some kind of derivative that you can take that will make it easier, or there's going to be some identity, trigonometric identity, which we might be using in today's video that can simplify it. So first of all, let's do integration by parts. And for the integration by parts, I'll be using the DI setup. And the DI setup is the exact same thing, except it's just a more visual way or a table-based way of taking the derivatives and integrals of the respective functions. So what we want to do, we want to integrate secant squared x. And integrating secant squared, we know that here also in this column we have a plus and a minus and a plus, let's say. Then integrating secant squared, we know we get tangent. And we're taking the derivative of secant x. The derivative of secant x is secant x tangent x. And what we do now within this DI setup is we take the product of the diagonals, and the row is always an integral. And that's why we see that this first row is the integral that we're trying to evaluate. And now when we take the product of the diagonals, then that means that this row will be the integral that we have to evaluate now. So this is an integral. So what we see here is now we get secant x tangent x, because that's the product of the diagonals, and then we minus, because there's a minus here, and that of course corresponds to the uv minus integral of v du in the traditional setup, minus the integral of, now we have a secant x tangent x multiplied by tangent x. So we have two tangent x's there, so that means we're going to have a secant x tangent squared x. And now what we can do is use a trigonometric identity, one of our favorites, that we know that the tangent squared of x is equal to the secant squared of x minus 1. Well, how do we know that? Well, you can derive this definition from the triangle, from a right angle triangle, or you can also derive it from the sine squared x plus cosine squared x is equal to 1 and divide everything by cosine squared x if you want to do it algebraically. And what we'll do now is we'll replace this with secant squared x minus 1. So we get that the integral, or we just get secant x tangent x now, and minus the integral of secant x, and we have now in brackets secant squared x minus 1. So what we see here is that we can distribute this bracket. We can distribute each term. So what we see now, and I'm writing this down on purpose, I'll say some variable I is equal to the integral of secant cubed x dx. And now what I'm going to say is that that is equal to all of this that we've worked out here. So this is equal to the secant x multiplied by the tangent of x minus the integral. And now let's distribute these brackets. So we have secant x times secant squared x, so that's secant cubed x. And then here we have a secant x times minus 1, so that's just a minus secant x, and we can put a dx. Now what we can do, we know that the integral is a linear operator, so we can split the integral. We know that the integral of secant cubed x minus secant x is the integral of secant cubed x minus the integral of secant x. So what we see is that I now is equal to, and then we have secant x tangent x, our regular stuff, and here I will look at this integral split up, but I have to take a bracket here, because we know that originally we're subtracting the entire integral, so we need to now take into account a bracket if we're separating them. So we have the integral of secant cubed x and dx, we close that, and remember we subtract now the integral of secant x dx. And of course this is the same, because if we join these integrals we see that we get the same thing. So now let's continue working on this, because the interesting we'll see when we once we distribute the negative to the bracket. So here we see that we get I is equal to, and we can already see it here, but let's just write this down. We have secant x tangent x. Now here we have a minus integral of secant cubed x, so I'll put that in this color here. minus the integral of secant cubed x dx. And this minus become a positive. So now we add the integral of secant x dx. And yes, I did that because what we see is that the integral of secant cubed x is our original integral, I. So what we really have here is just an equation where we have to solve for I. And this is the case where we have a repeated integral. So what we have is some I, which is the integral of secant cubed x, is equal to the secant x tangent x minus I, because I is the integral of secant cubed x. And if we just had a secant cubed x, of course that wouldn't work because I is defined to be the integral of secant cubed x. So here, and then we add the integral of secant x dx. And what we do, we treat this as a regular equation where we solve for I. So how do we do that? Well, we add I on both sides, and we see that this and this now cancel, and we get 2I because I plus I. And here, that's equal to the secant x multiplied by the tangent of x. Now we just have a plus the integral of secant x left. And what we know this integral because I made 2 videos on this previously, one using the Weierstrass substitution and one using an interesting U substitution. So here, what we know this to be is the natural log of secant x plus tangent x. So what we have now is that we get 2I is equal to the secant x multiplied by the tangent of x plus the natural log of the absolute value of the secant x plus the tangent x. However, we are not done because what do we want to find? We want to find what I is. This is our goal. However, what we have on our left-hand side is a 2I. So how do we solve for I? Well, of course, we just divide by 2. And after dividing by 2, we will get our final answer. So we finally see that I, which is equal to the integral of secant cubed x dx, is just equal to this part right here. And remember, we have divided by 2. So we have secant x tangent x plus the natural log of the absolute value of the secant x plus the tangent of x. And that's all divided by 2. And you can put a plus c because here we are done. So this was the answer, and this is I think, useful video if you're looking at these repeated integral cases, and I'll go over a few more integrals like these in my future videos. So that's it for today's video, and thank you for watching.